Assalamualaikum warahmatullahi wabarakatuh. We are from RAS 2132C. My name is Ahmad Kushairi.
And my name is Adam bin Shbaki Rosman. In this video, we are going to present Kepler's law of planetary motion and the law of ellipse. So, what is the Kepler law of motion? Kepler law of motion is a law that explains how the planet is orbiting around the sun. This law states that all planets are moving in elliptical orbit instead of a perfect circle orbit around the sun. This law clearly contradicts the first belief of previous people, where they believed that the planet Earth are the ones sitting at the center of the universe, while Sun and other planets are orbiting the Earth. On the history of how the Kepler's law was published, it started at the early of 17th century, where a German mathematician named Johannes Kepler produced three laws of Kepler law. The law that he produced, causing a groundbreaking in physics, where it changed completely our understanding of the universe by replacing the geocentric models and heliocentric models. Later on, Isaac Newton discovered that Kepler's law of planetary motion can be combined with his own law of motion. One of the laws that he produced is that all planets are moving around the sun in ellipse orbits. So, what is the Kepler first law? The first law states that all planets are moving around the sun in ellipse orbit instead of a perfect circle. By using these statements, we can obtain an ellipse equation to calculate the radial distance. Firstly, to get the equation, we must use the Newton's second law, where he states that the force that acts upon object is proportional to the sum of mass and acceleration. Hence, we get F equal to ma. Next, we construct the acceleration formula by combining both the radial force and transverse force. This can be produced by constructing the formula of acceleration from the polar coordinates. So we will get the formula of acceleration as given. However, during the planet's motion around the sun, the angular momentum are conserved, which means that there are no rate of change in angular momentum. It can be proven by transverse force equal to zero, since the gravity acts radially. From the formula is then, we use the product rule to derive and we get the given. Then we factor out the run so that we get the final product as r square theta dot equal to L. Next, by the formula of angular momentum, which is given by L equal to mr squared dot theta, we can substitute back the L equal to r squared dot theta, which we will get L equal to ml. Next, we introduce a new variable, which is u equal to 1 over r. These equations are an equation of orbit under the act of central force. Then we differentiate the r, which we will get r dot equal to negative u dot over u square. To obtain the u dot, we using the chain rule, which we will get du over d theta over d theta over dt. Since r square is equal to 1 over u square, by time the u square equal to 1 over r square, we will get theta dot equal to lu square. Next, we substitute back all the variable, which will be get r dot equal to negative L du over d theta. Then we differentiate again, which will get r double dot equal to negative L d over dt in bracket du over d theta close brackets, which will get r double dot equal to negative L square u square d square u over d theta square. So from all of that, we substitute back all into the Newton equation, which from the transverse equation, from the radial force equation, m in bracket r double dot minus r dot theta square equal to fr, we will get as givens. Then we simplify the formula, which will get d square u over d theta square plus u equal to negative f in bracket u power by negative 1 over ml square u square. This is the general differential equation of an orbit. So, from the inverse square, we need to obtain the ellipse equation. We know that the gravity equation are F equal to negative k over r square. So, from the previous equation, d square over u, d square u over d theta square plus u is equal to k over ml square. Since the right hand side is constant, we can assume as C, where C is a constant. So since U are also constants, when we differentiate U, we will get 0, which is as given. So we get C equal to K over ml square, or U equal to K over ml square. Then we use the homogeneous equation where U double dot plus U is equal to 0. This can be explained when if U are equal to cos, then we differentiate, we will get negative signs, and then we differentiate it again, we will get negative cos. This is also the same case with U equal to sin theta. We differentiate it and we get U equal to cos theta, and we differentiate it again, we get negative sin theta. So we see that both of them are the same. So we can just write as U equal to A cos theta plus B sin theta. By completing the equation, we will get U equal to A cos theta plus B sin theta plus K over ml square. Now, for the A cos theta plus B sin theta, we can use from the trigonometry identities, which will get C cos in bracket theta minus theta O, close brackets. So we will get U equal to C cos in bracket theta minus theta dot close bracket plus K over ml square. Since we need to remember that U are equal to 1 over R, so we can substitute it back into the equations. Hence we will get as the equation. In order to write a better equation, uh, we need to change the variable. So for the eccentric, or we call as E, is equal to CML square over K. Then we invert the equation, which will get R equal to ML square over K over 1 plus E cos in bracket theta minus theta dot.
So up next, we're going to talk about the application of Kepler's first law. Kepler's first law serves a lot of purpose in our daily lives. One of them is for satellite orbit design. Satellite doesn't orbit the Earth in perfect circles, but rather in elliptical orbit. The second one is for space mission path. Spacecraft travel in elliptical path to minimize consumption, mainly fuel consumption, and lastly, to predict comet's path, predicting the path the asteroid is going to take so that safety precautions can be taken early to ensure the safety of the planet Earth itself. So we're moving up to the example question. A dragonfly flying in spiral orbiting a bouquet of flowers at a distance of r equal to c alpha square. By assuming the dragonfly is orbiting under the central force as given by d square u over d alpha square plus u equal to negative 1 over ml square u square f u power of negative 1, show that the central fr is decreasing exponentially by the distance r. So the first step of this question is we going to change the r into u. As we know, r equal to c alpha square. Since u equal to 1 over r, we can replace r by doing u equals to 1 over c alpha square. Take out the alpha and we got 1 over c alpha power of negative 2. Next, we're going to find the first and the second derivatives. For the first and second derivative, we're going to differentiate the equation that we got. So firstly, we're going to differentiate du in terms of d alpha. We will get 1 over c negative 2 alpha power of negative 3. So simplify it, we will get negative 2 over c alpha power of 4. So the second derivative, we're gonna do d square u in terms of d alpha square, where we got 6 over c alpha power of 4. That is for our second derivative. So after we got the first and the second derivative, we're gonna put everything into the orbit equation. So the equation is d square u over d alpha square plus u equals to negative 1 over ml square u square fr. We're going to substitute it all together. It will become 6 over c alpha power of 4 plus 1 over c alpha power of 2 equals to negative 1 over ml square u square fr. So now we're going to replace alpha with r. Remember that r equal to c alpha square, then alpha square is equal to rc. And then alpha power of 4 is equal to r square over c square. So 6 over c alpha power of 4 is equal to 6c over r square, and 1 over c alpha power of 2 is equal to 1 over r. Therefore, it will become 6c over r square plus 1 over r equal to negative 1 over ml square u square fr. So next, we're going to use again u equal to 1 over r. Since u square equal to 1 over r square, then 1 over u square is equal to r square. We're going to multiply this on both sides, where we get fr equal to negative ml square 6c over r square plus 1 over r times 1 over r square. So we're going to simplify it, and we get fr equal to negative ml square 6c over r power 4 plus 1 over r power of 3, and that will be our final answer. In conclusion, Kepler's first law plays a major role in astronomical activities. It provides the fundamental geometric framework for describing and predicting the motion of all bodies in orbits. This law is not bound to planets in our solar system only. It also applies to moons, comets, asteroids, artificial satellites, and exoplanets. Its principles are embedded in nearly every astronomical observation and space mission. That's all from us. Thank you.